As we go forward, we're going to talk about prediction intervals and variation. So what we're going to do is, in the last section, we developed the line of least squares regression, and with that equation, we can predict a y value for an x value of interest, but that's only one point. So it's really more accurate to come up with an interval. So we are going to talk about prediction intervals, and that's a very important differentiation. So we are going to talk about prediction intervals, not confidence intervals, but prediction intervals. So what we're going to do is, for a value of x that we're interested in, we're going to find values that y would take about our regression line. The thing that we need to assume is true is we need to assume that the variance about the line of least squares regression stays the same. This is just a statement that needs to be true. We're not going to test for it, so don't get anxious over that statement. Now this is the equation that we're going to use, and it should look familiar. So our population parameter is going to be our sample statistic plus a margin of error, and our sample statistic minus our margin of error. Now, this formula for margin of error is quite interesting, but remember, we're going to use StatCrunch to do this, so don't break out in hives. And again, we are going to use technology, so remember that technology is our friend, and knowing that our standard error of estimate comes from our residuals, which is the difference between the actual y value and our predicted y value, is important, but we're not going to use that as, we're not going to do those calculations. Alright, so if we go back to our shoe print lengths and heights, we can construct a 95% prediction interval for the height. And here is our line of least squares regression. We found that in the last section. When we go through the dialog box, it says predict a value. This is what we're going to put in StatCrunch. And then all this other stuff will get our predicted y, and we will go forward using our printout. So here is our printout from StatCrunch, and it comes up with a 95% prediction interval, and it's important that you do the prediction interval. This CI is a confidence interval. That's a different thing, and we're not even going to talk about it. So when we look at this, we have the height of between 162 and 186 centimeters when we have a shoe print length of 29. And here is our predicted. There's our standard error, and our estimate of error standard deviation is up here. So those would be things that we would use if we were going to calculate it by hand. But isn't it wonderful we don't need to do that? This is a pretend line of least squares regression right here. And so it says our y-intercept is 3, our slope of our line is 2, and what we want to do is we want to look at these, and we're going to put in, the blue is the line, is our line of least squares regression, and we're going to assume that this is linearly, there is a linear correlation, and we want to look at our pairs of data, and then we want to look at our predicted value. So the 519 is our actual data value. The 513 is, the 13 is our predicted value. And then the 9 is our average y value. So the mean of the y values is 9. So that's why we have this horizontal line here. So here is what we're going to do. When we look at the deviation, we've got explained deviation and unexplained deviation. The total deviation goes from our predicted point down to the mean of the y's. And we would calculate that as part of our preliminary work. The unexplained deviation is between the predicted value, the actual value and the predicted value. And then the explained deviation is between the predicted value and the average value. This is r squared, or this proportion is going to actually be r squared. So remember, we said the proportion of the variation that is explained is r squared. And so that's the piece that we're looking for in this section. So we looked at our total deviation was 10. Our explained deviation was 4, and our unexplained deviation was 6. And we are talking about the variation here, so we're talking about this part right here. So if you wanted to calculate all this, you most certainly can, but it isn't difficult to find the total variation, because this is going to be right here is our residual value. This is going to be our r squared. And we can use those values to calculate this. So this is the important piece from this section. R squared is the explained variation, the amount of the explained variation divided by the total variation, or the value of r squared is the proportion of the variation in y that's explained by the relationship between x and y. And I've said that about 15 different times in the last lecture. In the last lecture, I couldn't remember that this was called the coefficient of determination. So r squared is also called the coefficient of determination. And sometimes in the literature, you're going to see it written as a capital R squared. It means the same thing. So here we go back, and we're going to look at the 40 shoe lengths, not the 5 that we used in the previous section, but we're going to take all 40 that were in Appendix B, and we get an R value of 0.813. So we square that, and we can say that 66.1% of the total variation in height can be explained by the shoe print length, but the other 33.9% cannot be explained by the shoe print length. The other 33% is due to other factors. Now, when we talk about this, we're going to sometimes you may see the definition marginal change, and we've already talked about this, but now they're going to give it a new name. The marginal change is the amount one variable changes with the other. So remember, we talked about the slope of the line. That represents the marginal change that occurs in y when x changes by 1 unit. Residuals, the difference between our observed y and our predicted y, is called the residual for that point. We're going to look at residual graphs, but we're not actually going to graph them ourselves. So here is an example. Here is our line of least squares regression. The 4 is going to represent our marginal change. So what that says is for every 1 unit that x goes up, y goes up 4 units. So the slope of our line is our marginal change. The residual is the difference between our actual y and our predicted y at that point. When it's below the line, it's negative. When it's above the line, it's positive. And usually if we're going to do any math with the residuals, we square them to get rid of those signs. And we already found the line of least squares regression, and that makes the sum of the squares of the residuals as small as possible. So what we do is we actually can plot the residuals, and it does give us some information, but we're not going to physically do it. So we want to look to make sure that there's no obvious pattern. We don't want the wideness of our plot to either widen out or to get thin. We want it to be consistent when we view it from left to right. So here is an example where there's really no pattern in the residuals. They're scattered. About half of them are above, about half of them are below. Now notice with this one we have an obvious pattern. We have this curve. Our straight line model's not a good one here because our residuals have a pattern. And here, in this part of our distribution, it's probably pretty good. But notice how it gets wider as we move to the right. So that means as our x gets bigger, our model is more weak. So this is, again, not a good linear model. So in essence, that's what there is in section 4. We looked for predictions and we found prediction intervals. We wanted to make sure we can interpret the regression equation, and that makes us think about our residual plots, look for the patterns there. Let's take a minute and we'll go to StatCrunch and we will actually do a prediction. So let's go ahead and let's look at how to do predictions. This is the data set 2 from the back of your textbook, and we're going to look at shoe print length and height, and we're going to do it for all 40 of these individuals. And so let's go ahead and we'll do stat, regression, simple linear. My x variable is going to be shoe print. My y variable is going to be height. I'm not going to do a hypothesis test, but I am going to go ahead and do a confidence level 95%. And here's where you put in your prediction. And we wanted to know if our shoe print length was 29 centimeters, what's going to happen, what's going to be the rest of our value. Let's compute. And this is what I had pasted into the slide. So here we have our dependent variables, height, independent shoe print. Here's our line of least squares regression, our correlation coefficient, our coefficient of determination, standard estimate of our error standard deviation, and as we go down, here we have our prediction interval right here. And so that's how you would do that. My predicted x value is 29. The x value I was interested in was 29. My predicted y is 174. So we would do it in a similar manner. We can also go to our graph. So here's our line of least squares regression. You can see about half of the points are above, half are below. So just to give you an idea of what that's going to look like.